Hello, everyone. This is the second session of the day in QCrypt 2021. So we have three different presentations. The first one is actually two of the presentation merged together. So the first one is by Obada earlier from University of Bristol, and then it's merged with Fadri Grunenfelder. So you'll see these talks, and then you may have questions. So please post your questions here, raise your hand here or in the Slack channel. So you'll be following after the presentations. So now to Obada, please.
Hello, everyone. Can you see my screen?
Yeah.
Yeah, perfect. Hello, everyone. My name is Ubad Alia, and I'm a PhD candidate at the University of Bristol, Smart Internet Lab. So today I'm going to talk about the coexistence of quantum and classical channels in Holocore fiber. The vision behind this work was to provide a seamless coexistence medium in which we can coexist both the quantum and classical channels without having a major effect on the quantum channel performance. So the medium, any coexistence medium, could be used for quantum cryptography applications such as QKD or distributed quantum computing. And if we're going to use the separate multiple fibers for classical and quantum channels, it's going to be extremely impractical for large quantum network. So far, we've been using single mode fiber for coexisting, and this limits the coexistence due to two factors. The first factor is the nonlinear effects in the single mode fiber, such as Raman scattering and four-wave mixing. And the second thing is the loss of single mode fiber has been 0.20 dB per kilometer since 1979. We believe Holocore fiber can be considered as the ultimate medium because since the light travels in a Holocore, it has extremely low nonlinear effects, which really affects the quantum channel performance, but also it has the potential of having extremely lower loss, 10 times lower than single mode fiber. So this slide shows the journey of the losses of the Holocore fiber. As you can see, from 2015, it goes down from around more than 100 dB per kilometer, all the way down to 0.20 dB per kilometer recently, which is quite similar to single mode fiber. This design mainly called Holocore nested anti-resonance lossless fiber. And I'm going to be focusing on this design, which was used in this experiment. So as you can see in this design, there are 6 nested tubes. And since the light travels in the Holocore, it has low nonlinear effects. And we can have the Holocore fiber as a single moded fiber if we match the higher order modes with the phase of the membranes around the Holocore. This figure on the right shows us that the simulation of the loss. And if we can increase the core size, potentially we can reach the loss that is 10 times lower than single mode fiber. And why this is quite important, because as you can see here, there are matching between the red and the black line. The red line was the simulated and the black line was the experimental. And the matching here is in the C band and the L band. So potentially, if we manage to follow this trend, we will be able to get an extremely low loss Holocore fiber. This here on the bottom right corner, I'm showing this a new design by the Optoelectronics Research Center at the University of Southampton, which they use 5 nested cores around the Holocore. And this provides us with a loss around 0.20 dB at the edge of the L band, which is similar to single mode fiber. This shows us the experimental setup of my system. The main point here is to focus on the double filter stages of the classical channels, because it's very important to filter classical channels very well. So if we filter the classical channels and multiplexing using a WSS, we used a sharp edge Ionista filter, tunable bandpass filter. We coexisting them using a WDM multiplexer, goes through the fiber in a coexistence configuration. split them, and the quantum goes to the Bob QKD unit, and the classical goes back to the Rx for a coherent detection. This figure shows us the result of the multi-core fiber. As expected, when we increase the power and the number of channels, we can see the secret key rate performance goes down because of the more noise photons are leaking to the Bob QKD unit, to the point where we got almost 100 bits per second when we have 4 channels at 9 dBms per channel. However, for the Holocore fiber, the results look something like this. When we increase the power of the channels or increase the number of channels, there's only a minor effect of around 10% lowering the secret key rate. This really shows us that Holocore fiber could potentially be used as the ultimate medium for quantum classical coexistence, especially at an extremely high power. That's the end of my talk. Thanks, everyone. And please, if you have any question, just let me know.
Thank you, Ubaida, for this short talk. Now we are moving to the second part of this talk by Fadri Grunenfelder.
Okay, hello everyone. Can you see my slides?
Yeah.
Okay, so welcome to this second part of this merged talk. My name is Fadri Grunenfelder, and I'm a PhD student at the University of Geneva in the Quantum Technologies group. And today I will talk about how we can multiplex a 2.5 gigahertz discrete variable QKD system into a small network environment. So the network we considered is shown here. So on one end we have the QKD system of Alice, and on the other hand we have the QKD system of Bob. Alice uses 1310 nanometer light for the encoding of her states. And additionally, we have 13 channels of like classical communication, which are around 1550 and multiplexed into the same fiber link. And for the fiber link, we have two choices. Either we take 95.5 kilometer standard single mode fiber, or we take a shorter one, which is 51.5 kilometers, but which is interrupted by some additional attenuation. And the two channels have roughly the same loss, but this one is considered a bit more realistic for a network because we have a lot of connectors and other devices in the network which will introduce additional losses, not only the fiber itself. And now in such a scenario, the most important question is what is the maximum classical launch power we can tolerate for the QKD system to still exchange a secret key, since you have, for example, Raman scattering or other noise degrading our quantum signal. And in our experiment with 95.5 kilometer channel, we could show that we could distribute the secret key rate up to 8.9 dBm of total launch power in all the classical channels, or total launch powers as the sum of all the power of the classical channels. And additionally, we also did the experiment with the other channel, which is shorter but has the attenuation. And there we can see that we can perform even better. So we could go to about 16.7 dBm. And with this, I already conclude. So with our experiment, we could show that we could perform a secret key exchange over this 95.5 kilometers of fiber up to a classical signal launch power of 8.9 dBm. And additionally, we did a simulation where we simulated our system, but with ideal laser pulses, with ideal filters and perfect detectors. And it turns out that, or our simulation suggests that we, in this case, in an ideal case, we could go up to 27 dBm launch power for this 95.5 kilometers. And now let me quickly tell you what I will talk about a bit more in my complete talk. So I will compare 1310 nanometer and 1550 nanometer for the quantum channel wavelength. I will describe the QKD system we used a bit more in detail, and I will compare the results we got to previous studies. And with this, I would already like to thank you for your attention, and I'm looking forward to your questions later on.
Thank you, Fredrik, for this talk. And then, so please leave your questions to the Slack channel, or here, raise your hand here. So we'll address that in the end of this presentation. Now we are moving to the second presentation here. Over to Alvaro.
Can you see my presentation now?
Yes, go on.
Okay, so good morning, everyone. My name is Álvaro Alarcón, and today I'm going to present my work title, Minimizing Detection Losses from Time-Beam Quantum Cryptography System with Few-Mode Fiber Technology. So a natural selection for quantum communication is to use the relative phase between two paths of a single photon. One of the best known system is the phase encoding scheme, as we show here. We can separate the analysis of any quantum system with the transmitter, that is Alice, the receiver, Bob, and the channel. The idea here is try to create this phase encode qubit in the Alice side. Then this state will propagate through this channel consisting in two single mode fiber links. Then Bob will make the projection in this fiber coupler or the beam splitter. Both beams will arrive at the same time, and the output probabilities are proportional to cosine square, sine square, and the difference between the phase applied by Alice and Bob. The drawback is that the long interferometers are needed. So complex and many times unpractical stability control systems are needed too. It's for that reason that time beam encoding arises as a solution for this drawback. Now, instead to have a long interferometer, we have two shorter unbalanced Mach-Zehnder interferometers in the Alice side and the Bob side. Now we have one length path and one short path. And here, both pulses are propagating together, but now just in one single mode fiber link. Bob will make the projection in the final fiber coupler as well. And now we will have 3 time slots when the pulses will arrive. This system has a huge advantage compared to the previous one because now it's easier to actively stabilize the system because we're acting on 2 shorter interferometers. And also we are using just one single mode fiber link. But the trade-off of using time beam is that we must discard information. In this case, we need to discard the 50% of the information because the early and late beam are distinguishable to each other, so they do not interfere. And this problem increases when we scale in the dimensionality of our quantum system. It's for that reason that we have taken advantage of 2 key elements of a spatial division multiplexing. One of them is the use of few-mode fibers. In our case, this fiber is able to transport 3 different spatial modes of propagation, LP01, LP11A, and LP11B. The other component is the photonic lantern, a device able to take single mode at the input, and the lantern can map each one of them in higher modes at the output by using the same few-mode fiber. So by using those 2 elements, we can map a qubit with path information to another qubit with spatial information at the output. So our proposal is a few-mode fiber interferometer configuration. Here in Alice and Bob, we also have 2 shorter interferometers, but both paths have the same length. We're using photonic lanterns in Alice in order to create this coherent superposition, and that will travel now in one fiber link, but now it's a few-mode fiber link. we can know that for some values of phases, we can get the OIM modes, highly desirable in optical communication and quantum communication as well. Then Bob will make the projection in the final fiber coupler or beam splitter. The output probabilities are proportional to cosine square, sine square, and the difference between the phases that Alice and Bob applied. But now no post-selection is needed since the pulses arrive together. So we can remove the intrinsic losses of time beam. So in order to show feasibility of our system, we want to show the interference pattern at the end in the detectors. So we can see here what happened with Bob apply a constant phase equal to 0 and a constant phase equal to pi/2. Meanwhile, Alice is changing the phase between 0 and 2 pi continuously. We can see that both outcomes are proportional to sine square and cosine square, and the maximum and minimum values will depend on the phase difference between Alice and Bob. At the right, we have the matrix with the projection when we prepare some state in Alice and we project in the corresponding state in Bob. We can see that the average probability of the main diagonal, that is when we prepare one state and we measure in the same state, is roughly 95%. This is after 500 meters too. So now that we have the platform, the next task are perform a complete QKD session, increase the transmission distance, and expanding the setup to higher dimensions. So thank you very much for your attention.
Thank you very much, Alvaro, for this presentation. As always, please post your questions in Slack channel or raise your hands here. Now we move into the last talk of the session by Jasmine Destinder, please. Hi, Jasmine, we cannot hear you.
You can hear me now?
Yes, now please.
Sure. Okay. So I'll give a quick overview in some of the results in finite key effects for satellite quantum key distribution. So typically we use satellite quantum communications are attractive because it helps overcome direct transmission limits, but also extends quantum networks, which is useful for a lot of distributed applications in quantum networking. So if we have a look at a general satellite overpass geometry, we have some altitude h, which the satellite overpasses, and instantaneously it generates a ground track offset, which is given by this green line. And the maximum, or rather the minimum elevation or past which the secret key length attainable is 0 defines the overall key generation footprint for the SAT QKD system. So we start by first defining something called the system link efficiency. This characterizes the performance of our SAT QKD system, and it's the link efficiency between the satellite and the OGS at zenith. So that's the highest point the satellite is at its trajectory. And we construct a representative link efficiency curve using empirical data that was published by Missius. So here we have the link efficiency with elevation or time, with the peak being at, or rather the minimum being at 27 dB. And what we can do to model different SAT QKD systems is linearly scale this link efficiency either up or down, depending on what we want to model. What we also do is we categorize different errors associated with different parts of the system. So for example, the source errors, that includes non-ideal signals, any misalignments or imperfect projective measurements. We also characterize we have another term which we call the extraneous count errors, which includes dark count rate, background light. And so we'll have a look at how these two different terms interplay in terms of the attainable secret key length that you can get. So we implement an optimized decoy state BB84 protocol. So we optimize over the protocol parameters that include the intensities, their probabilities, also the basis encoding probability, but also the overpass transmission time. And the importance of the last optimization is because the atmosphere is really a highly variable channel. So what this means is data from low elevations has both small count rates and higher quantum bit error rates. And so there's an important trade-off between the amount of block size that you accumulate and the data quality. So just to have a look at that for a particular overpass, we impose a minimum elevation constraint, which we take to be 10 degrees in our work here. And we typically construct data to be in this blue region. So these are where the high quantum bit error rates, we basically disregard those. And if we have a look at the attainable secret key length with different time windows, dt about the highest point, the zenith point, what we typically see is for low system link efficiencies, it's better to construct keys using the greatest amount of data. So taking the satellite to be close to the horizon. But for high link efficiencies, then use data around really only just the zenith. And that's because of the better average quantum bit error rate and also which count as small raw key length and larger statistical uncertainties. So this optimization, we've written this up in a Python package, which is now available on GitHub to download. We call it SATCUMA, or Satellite Quantum Modeling and Analysis Software. And it gives us a toolkit to model different SAT-QKD systems, and we're hoping to extend this using like implementing different protocols such as CV. So this is stuff that we're working on, and if anyone's interested, do get in touch with us. So just to have a look at some of the applications, have a look at the extended recording of this talk or the paper, which is available on the archive. But some applications that we can use SATCUMA for is to see the relative system performance. So this comes back to the extraneous count error rate and also the intrinsic QBER. So what we see is that it is better to improve the background light suppression and detector counts over source fidelities. So this kind of gives us a direction in which future SAT-QKD implementations should really focus their efforts. In addition, what we can do is evaluate what the expected annual finite key is annually. And so here we plot the secret key length versus different ground track offsets for different overpass geometries. And we see is that for 27 dB, we have 0.9 gigabytes of finite key that's attainable annually at point of Glasgow, so that's a latitude of 55.9. And at 40 dB, which is more likely of losses at SAT-QKD operation, we get quite a small finite key. And one way to improve that is really to accumulate larger block sizes, which you can do by using data from multiple overpasses. And that's what we plot here. So we have a look at the effect of increasing the block sizes by using data from multiple passes. So we consider 3 different systems, which comprise different values for your system link efficiencies, extraneous count, and intrinsic QBERs. Where for one overpass, we have 0 key, but we see an increasing number, an increasing finite key per pass. And this improvement really is due to the smaller estimation uncertainty errors that feature in the finite key. And one thing that should be regarded is the greater latency, which leads to potential security vulnerability. So there are more applications in the archive version and the longer talk, but that's all for now. Thank you very much.
Thank you very much, Jasmine. Now we have a few questions. So the first one from Mohsen Rosavi, could you please unmute and ask?
Hi, thank you. So this is the question for Fadri. So there are some theory work that suggests that if you place the QKD channel in the dips of your Raman spectrum, you may still get some positive key rates. I wonder if you ever tried those configurations that instead of mixing the QKD channel with the CWDM multiplexer to just include it as one of your DWDM channels and see if you can get any key rate.
Yeah, there are, I think there are already a few papers. So then you have basically in what you, in the idea you suggest that you would have the quantum channel also close. I mean, very close to the classical channels. No, because the dips in the Raman spectrum, I think they're only about 1 nanometer apart from the wavelength, center wavelength of your classical communication. And I think people already looked at this. But the problem is now if you start to have multiple classical channels close together in this DWDM configuration, then the minimum, I mean, you start to have overlapping Raman spectrum, and the minimum kind of gets filled up by the other channels. I don't know if this was clear. But...
no, I understand, but still the theory suggests that there are regimes of operation that you can get some key rate. I was just wondering if you ever tried experimentally to see that actually happens at much lower launch power. So it probably instead of 9 dBm, you might need to go to below 1 dBm.
Yes.
But there are some regimes of operation that could be possible.
Yeah.
So I was wondering if experimentally that has been verified.
Yeah, I mean, there is a paper by our group, but it's already much older. So it was done by Reds, and it's, I think it was before, probably something like 2012 already. I'm not really sure about the date. But yeah, also other people investigated this. And I mean, as you said, it works, but only for lower launch powers.
Okay, thank you.
Thank you, Petri. So now we have Levi Emilian. So could you please unmute and ask your question, please?
Yeah, thanks. I have a question to Alvaro. Basically, you presented this component, the photonic lantern, and it looks very interesting. The way I understand it is that it's kind of like a switch. You have inputs, as input, you have spatial modes, and you just redirect them to modes on the fiber. So basically, my question is that whether there are some limitations using this component. For instance, maybe there is a maximum number of modes that you can convert, maybe due to energy constraints. If you have too many modes, probably you would burn your component. Also, if you have limitation on the repetition rate and on the conversion efficiency. Thanks.
Yeah, thank you so much for that question. And it's not like a switch. Actually, this is most like a converter, actually. So in our case, we have a lantern with 3 different single mode fiber inputs. They are labeled as 1, 2, and 3. If we connect light in the first port, we can map the Gaussian to the Gaussian in the few mode fiber. If we connect the second one and the third one, we will have LP11A and LP11B correspondingly. But there are another kind of photonic lanterns with 6 inputs or 12 inputs, I think. So it depends where we are connecting our laser, we will have some modes in the few mode fiber at the output. If we connect 2 at the same time, we will have a kind of superposition in the output. So the limitation for now is just the number of inputs, because this is a passive device, it's not active. And if I forget your last question, so if you can repeat me, please, Levi.
Yeah, so okay, basically, if you have other limitations, for instance, on the conversion efficiency, but I think you briefly mentioned it, if you have a superposition, it's maybe kind of degrading your input, since you have like a mixture as output.
Yeah, we have some limitations because that conversion is not uniform. So we will have more losses when we increase the dimension of the modes. So we need to compensate that difference in power at the beginning, so at the input of the lantern. So for now, our main limitation is that we need to have the proper detectors at the end in order to fight against those losses that we will have at the beginning.
Okay, thank you.
You're welcome.
Okay, thank you. Thank you, Alvaro, for answering that questions. Now we move to a question from Andrea Pope. Andrea, please. please unmute and then ask.
Hello, can you hear me?
Yep.
Yes, okay, very good. So one question to Yasminda. So which source reparator on the satellite did you use for your calculations? Because for the annual key rates, you showed absolute values.
Yeah, so we used 100 megahertz. This was based on the original Missis implementation, but they have recently upped it to 200 megahertz, if I'm correct. And we have rerun some of the plots to incorporate like what the effect of increasing the rep rate is. So this is some of the applications that, you know, SAP-CUMA can do, but it didn't really go into the 5-minute presentation.
And which kind of orbit did you choose for your calculations? Was it LEO?
Sun-synchronous orbit with altitude 500 kilometers.
Okay.
So yeah, basically just doing what Missis, you know, just yeah.
Thank you.
Okay.
Thank you. So if I may ask a question to Obeda. So you were talking about this Holocore fiber thing. So what will be the future? Will we have this Holocore fiber deployed? I mean, can we have a field demonstration at some point in future? What is the future that you are doing this work in the lab? Will it go to field? That's my question.
Yeah, that's a good question. BT is already actually doing a field deployed Holocore fiber with a spin-off from the University of Southampton. I don't think this will be used for quantum. It's going to be used for normal communication 5G because it's low latency. It's still an active area of research. If we manage to get the losses of the Holocore fiber and manage to fabricate the fiber in extremely long length, like more than, because now I think the longest is 8 kilometers, which is not good enough to deploy it, we might be able to use this Holocore fiber in a field deployed fashion. So it's still fairly new. 5 years ago, the losses were above 100 dBs per kilometers. Now it's 0.22 dBs per kilometer. So yeah, in theory, if we manage to get the losses down and manage to fabricate long fiber at a cheap rate, I don't see why not, but it's still an active area of research and we just need to wait and see, basically.
Perfect, thanks. And that's all for from this session. Thank you for the participants and thank you for the attendees. Thanks a lot.